have any background on this can follow along. So we are going to first talk about quantization very briefly, group-wise quantization, low-bit packing, then actually talk about the low-bit group-wise quantized linear operator, and then we're going to get into the demos, right? And then after the demos, we're going to do some code. We're going to go through the code. Right? So my intent, I guess, is that so this would be sort of the metric to know if the talk is successful. Anybody listening to this, they should, at the end of the talk, I should have given enough material, so enough context, so that if you want to actually contribute to the development of these kernels, then you can do so, and you know where everything is located, and you understand enough details to be able to do it. Right? So let's get into it. Very briefly, so quantization is basically a technique to map floating points into a small range of integer values, and it's done to reduce memory, right, and speed up computations. It's very the more common would be like int8, uint8 quantization, right? So for example, with uint8 we map floating points to 8-bit unsigned integers in the range from 0 to 255, right? So then, for example, if you're talking about a float 32 that takes 4 bytes, you'll be sort of like codifying each one of them with one integer with one uint8 integer that only takes 1 byte, right? In low-bit quantization, we go even lower, right? So we want to codify each floating point with just bits, few bits, like 3 bits, 5 bits, right? So basically that's what it is. We are mapping the floating points into the n-bit unsigned integers. So then that the range will be from 0 to 2 to the n-1. So for 4-bit, it will be from 0 to 15. From 5-bit will be from 0 to 31, right? So yeah, so then you get even more compression. Now at this point, that's why I said there was going to be a few demos. I'm going to go out of the slides, and I'm going to go here just very briefly to actually understand what is quantization doing, right? So so let's give an example of quantizing at just 10 element array using 5-bit quantization, right? So we just start with our array, right, with floating points. Each one is of the name float 32. The first thing we need to do is we need to determine the scale and the 0 points. To do that, what we do is that we compute the range, right? One way of doing this, right? There are other ways of doing it, but one way of doing this would be to just compute the range of the array. So in this case, this is 8.11, right? So it goes from minus 3.2 to 4.91, right? Then what we do is that we divide that range by the amount of values that we have that we want to that we have at our disposal. So if we're doing 5-bit quantization, then we have 32 values, but we divide by 31 because we divide by 31 because we actually, it's not the values, but it's like the steps, right, that we are taking every time that we increase the scale. So we divide by 31, we compute the scale. In the case of uint8, we'll be dividing by 255. And then we compute the point that would be mapping to so like the value in quantized space that maps to 0, right, to the 0 in the floating point space, right? And we want that one, we want to map that exactly. So we actually, after we compute the 0 points, we actually based our calculation of the quantization based on that 0 points, right? So to apply quantization, we'll have to, we divide our array by the scale, we add the 0 points, we surround, clip by the extremes of our range, and then sort of our quantized range, so Q min, Q max, and then that's it. We have here our array, right, of quantized values. So you see, we have it goes from 0 to 31. Those are the maximum ones, because we're using 5-bit quantization. If this had been 8-bit quantization, then we would be seeing here like something from 0 to 255, right? Values in that range. Just to see, it's like when we quantize, we actually lose precision, right? So just to see how much precision we're talking about in the case of, in this case. So we can do this to dequantize the array. If we print the to compare the values, then this is what we see, right? So we these are the values that we started one, like, to the left at 1.21, 2.34, right, over here, and these are the values that we would be we would think they are if we dequantize the quantized values, right? So I mean, I guess everybody, not everybody, but most people are familiar with this, but I just wanted to go over this real quick. So that's quantization. Now, if we do this over an entire tensor, right, that has a lot of values, the scale will depend on the range, like from the minimum to the maximum of that entire tensor. The tensor has like 1 million elements. Then the precision is going to be worse, right? So one technique that is used is called group-wise quantization. So you don't quantize the entire tensor, you just quantize pieces, right? That you quantize it by groups. So, and one way of doing it is, for example, in this case, I'm using a 2D case because it's what we're going to be working with. So we take every row, right, and then we divide it in groups, right, of a given size, right, and then so let's say 32, right? So we take groups of length 32, and then we just quantize each one of those, right, groups, right, separately. Now, when you do that group-wise quantization, so what do you end up with, right? You started with your original tensor that is floating point tensor, and then the output is going to be a quantized tensor of the same shape. It's just that before you had floating points, now you have integers, right? But then because you're doing it group-wise, every time that you quantize one of these arrays, you are producing one scale and one 0 point. And you need those to continue doing all the computations, so you need to store those. So you end up with these scales and 0 points tensors, right? And in this case, so in this example, right, we have an 8x8 tensor, right, that we use groups of length 4, right? And then, so we have 2 groups per row, so we end up with 8x2 tensors for the scales and the 0 points. Is that clear? Good so far?
Yeah, so maybe we should maybe sort of clarify why people need to do this. Like, I figure maybe your previous notebook was quite nice, and maybe if we show people like anomalies, like basically sort of like large values and what happens to them when you quantize and dequantize, people might better understand the intuition of why group-wise quantization is important.
Yeah. Oh, so you want to like play around with this and like put like something like 1,000 here or something like that?
Yeah, like it's just so people understand like why the notion of groups is important.
Right. So, well, yeah, if we do something like that, then our range is going to be really large. So when we do, yeah, that's a good call, Mark. So the scale is going to be really large, right? So let's just continue doing this. So we get to the end. Are you going to see when we dequantize back, we're going to lose? Yeah, you see, we lose a lot of yeah. This is now garbage, right? So yeah.
So this is why like basically like group-wise is interesting, but like of course group-wise is slower because you have to you have multiple scales and factors, you need to store them, you need to do this like group-wise operation, so everything's just more complicated, but you have to do it, unfortunately.
Right. So, but yeah, that's actually a very good call. All right, so we were on group-wise quantization. Now, in the case of so when we are doing uint 8, we are done here, right? But when we are doing low-bit quantization, right, this operation here, what it produced is actually a tensor, right? That, so let me see if the next slide. Yeah, so the quantized tensor, right, has, so in the case of, for example, 5-bit, the quantized tensor will have values between 0 to 31. Like each number will be a value between 0 to 31, but they are stored in bytes, right? You may be using a uint 8 dtype. Now, this is not, I mean, we want to actually completely like squeeze this into the minimal amount of space that we need to store this, right? So this is where packing comes in, right? So in this example, right, so where we have an 8x16 quantized tensor, each cell has, it has an integer that has 5 bits. So you really only need 5 for every row. You only need 5 times 16 bits, so 80 bits to represent that entire row. And you can, you only need 10 bytes for that. So you can store that in an 8x10 tensor with D-type uint8, right? Now, every cell now on that packed tensor is not going to directly map to a number from the quantized tensor. It's just basically like the bits are being packed right there. Using just more generally, right? Like if the quantized tensor is n by k, and we have n bit values, then we are using n times k bits per row. We divide by 8 to get the bytes. So then the packed tensor will be n times by n times k divided by 8. So this will be the shape, the resulting shape of the packed tensor, right? So we started with a floating point tensor, right? FP32, FP16, and then we quantized it, and then we packed that, and then now we end up with this packed tensor, right? Now, so for simplicity, right? And I say so for simplicity because depending on the n, you may not impose this requirement. But for simplicity, we require k to be a multiple of 8. And this, in all of the cases that we work with, we always have like, k is a multiple of 32 at least, right? So, we always pack, and another thing important to think about packing is that we always pack 8 values at a time because, well, if you have 4 bits, you don't need to, you can only pack 2 at a time. But more generally, if you're thinking about 5 bit, 3 bit, you are packing 8 values because 5 doesn't divide 8, so you can't really. You have to actually use 8 values. You're transforming. 8 bytes, you're basically mapping 8 bytes to n bytes, right? So in the case of 5-bit quantization, low-bit packing, you'll be mapping 8 bytes to 5 bytes. In the case of 3 bits, 8 bytes to 3 bytes. So now, okay, finally we are able to arrive after, I don't know, about 15 minutes. We can arrive to the actual operator that we're going to be, the operators that we're going to be talking about. So we're going to be talking about low bits, where low bit is because we're talking about values of n from 1 to 7. Group-wise quantized, only the weight is what we are quantizing. So group-wise quantized, weight-only linear operators, because these are we are implementing the linear, but using these packed weights, right? So then the signature of this op will look like this, right? So you have your first tensor will be like the activations, right? In this case, it will be a floating point tensor. The name of this operator is like this because you can read it like linear floating point activations n bit weights, right? So B would be this packed n bit packed weight tensor. Then you have the group size that you used to quantize your tensor. And then the tensor containing the scale and the tensor containing the zeros, right? So the scales and the zeros. So let's say that we are using m, k, and n for the dimensions here of linear. So the activations will be n by k. The pack weights, as we saw, will be n by n times k divided by 8. And the group size that we use, we allow either 32, 64, 128, or 256. And then the scales for each group, they are k divided by g, because you for every so like the rows are dimension k, you have to divide that by the group size, right, to get the number of groups, which will be the number of scales on each row in the scale tensor. And the same thing for the 0 points, right? And here, this is a ceiling because we don't really need, so like we can handle cases where G doesn't divide exactly when G is not an exact divisor of K, right? All right. So let me know if you have any questions at this point. Otherwise, I'm just going to jump into the first demo.
Yeah, I think this is clear. We can just jump into the demo.
All right. So let's. So I'm gonna. First of all, I'm not gonna run. I'm not gonna run this right now. These things, but these are the exact commands that I ran to install. To install these operators. So we clone AO. I'm creating a new environment. I'm installing some dependencies. Parameterize, I'm actually installing just because I for some tests. But the main thing here is that when we are installing AO, we have to do it this way in order to get this. So these are experimental ops right now. And if you just do pip install torch AO, you're not going to get them. You have to install locally, and you have to use these two flags, use cpp =1 and torch build experimental MPS =1 to get them, right? These are the things that I ran. I ran them because I'm using them in the demos, not necessarily for the operators themselves. So this is how you would install it in your Conda environment. Yeah, let's jump into demo 1. So the first thing that I want to show is this whole process that I explained on the slides. Let's do it here, right? So the first thing is that we're getting some weights. We want to quantize them, right? So the first thing we need is to import. We need to import the quantize function from torchio.experimental.quant API, right? That's what is implementing this low bit quantize operation, low bit quantization. So I have a script here, generate data, that I generated weights such that when I quantize them and then dequantize them, I actually get back the same numbers. And I did this so that we can compare this then later to linear. So and actually have that satisfaction of actually getting the same numbers, right? So just assume that we're getting weights from somewhere. Let's say that we are loading them from some place, right? And in this example, we are using NBD = 5, and let's use these dimensions, right? Small dimensions so that we can actually examine these tensors easily, right? So let's examine the weights, right? So the weights are this. They are so I'm printing here the shapes, the types, and bytes. So basically, they are. This is an 8x64 float32 tensor. It takes 2048 bytes, right? And I'm computing the bytes just by multiplying the number of elements by 4, which is by the number of bytes that each number occupies, right? So yeah, it is a utility function that I had here. All right. So now that we have our weights, let's quantize them first. We're going to use quantize to quantize them. In this case, so what we need to pass to quantize is the weights, the group size, the n bits, right? So this case is 5 in this example. These operators, we are using zeros because there are the CPU operators. They have options where you don't need the zeros, but these ones do. And then we are using uint8 quantization, so its sign is false because we are not using int8, we're using uint8 when we are doing this quantization, right? Sorry. So by that I mean that we are doing n-bit quantization, so like 5-bit quantization, but we are storing the values in uint8 tensor. So the quant weights tensor that we're going to get is uint8, right? So let's examine the scales. This is what we get back. Nice scales because that's why I prepared this data so that these things would be nice to see. And the zeros are these ones. Notice that the zeros are between in the range 0 to 31, right? Now we examine the quantized weights. It's like I said, it's a torch uint8 tensor. look at all of the values here. They're all between 0 and 31. And let's see. So the shape, 8 by 64. So the shape hasn't changed. The type is eventate, and the number of bytes is 512. So that went down now by 4 because we were using 2048 bytes, but we were using 4 bytes for each number. Now we're using a single byte, so that went down by a factor of 4. Right?
So Manuel, actually, before we keep going, so we have someone in chat, like Noah Peterson is asking, is this inference only, or can you also train in low bit?
This is inference only.
So could you maybe talk about like some of the trade-offs then? Because like I think, for example, for like we had a previous speaker, Goners, to talk about quantized training. Like essentially the complexity are like you need basically low bit, like basically you need the low bit like gradients, you need the low bit like backwards pass implemented. And then because that has like major correction issues, major error issues, you need something like stochastic rounding to really make this work. But I guess maybe what might help is you can also talk about the motivation behind those kernels. Like presumably, like this is also for phones, right? And maybe this can connect.
Yeah. So basically, the idea here, these kernels are the main motivation is to be able to run Llama and LLMs on device, right? So as the models get bigger, we want to run them on our phones. We want to run them. So these kernels, they were landed. I'm going to touch on that when we are on the code on the part of the code, walking through the code. But so we are ready before working on these kernels. We already have had in PyTorch. We had the int like 4-bit quantized linear. So basically the same, not exactly the same, but basically the same idea. 4-bit quantized linear on like I think the first one that was landed was for the CUDA backend, and then for the MPS backend. That was on PyTorch, but we want to also utilize these kernels in executors. So I have here a few. I'm gonna when I go through the code, I'm gonna show you how these kernels are being integrated into each one of these places, right? So how they are integrated into Torchad executors. I'm gonna talk a little bit about that. But so basically, the motivation is so that we can run them not only on Macs but also on iPhones or Android, right? So any devices, right? So there are models that you really need to go to 4 bits and even to 3 bits to be able to run them at all, right, on these devices. So that's the motivation here, and this is why the emphasis on inference, because at this point when you are training on device is also a thing, but inference on device is what we are at least I am working on.
So by the way, Mel, I'm sort of curious because like at least for MacBooks, like generally, for example, for GPUs, like you have 40 gigs, you have 80 gigs, you have 100 gigs on the Blackwells.
Right.
So these are like useful numbers. Like for Mac, I think it ranges from like 48 to 128, like of unified memory. Like how much VRAM are you really working with on like?
So right now, this machine that I'm working on, I have 16 gigs.
16 gigs. Okay.
This is an M1 Pro. This is actually my personal machine, and the reason I'm using my personal machine is because my personal has less RAM than the work machine.
So you want to really make sure it works.
Yeah. I'm actually going on this. Yeah. So yeah, this is an M1 Pro from 2021, I think, and it has 16 gigs. Yeah.
I see.
Yeah. So yeah. So it's not an M1 Max with 64 or an M3, but no. So it's very small, right? So
okay.
In comparison, right? So we were on. Okay, so yeah, we had already finished quantizing the weights, and now we are going to pack them, right? And so the operation that now we're encountering our packing. This is also a kernel that we have in Tercio that we made for this, and it's packing the weights specifically for this linear operator, right? We're packing the weights. We have this same version, but with 1 bit, 2 bit, 3 bit, up to 7 bit. And then now let's examine the pack weights. So the shape is now reduced to 8 by 40, right? And why is that? Because in this 64, each group of 8 is being now condensed into 5. So now you have, like, instead of 8 by 8, like 64 is 8 by 8. Now you have 5 by 8, which is 40, right? So that's why you now have a tensor that is 8 by 40. And the D type is still uint 8, right? Because you are packing these bits into uint 8 values. And how many bytes we are using? 320. So 512 went down to 320, right? So we have our packed weights. Now we're gonna use now the linear operator. And to do that, we need to prepare the scales, because they accept. So basically, one thing we do with the zeros is that the zeros that we got from quantized are integers, but we are actually going to be, when we are quantizing, we are actually multiplying the zeros by scale. Like, we are adding the zeros, or subtracting the zeros, sorry, and multiplying by scale. So then we already do that computation beforehand. So we just do the zeros equal minus zeros times scales. And then our operator is taking them transposed. So we also do this. And so basically, we end up with scales and zeros that look like this, right? So now we move everything to the MPS backend. So now we have our part weights, our scales and zeros. We're going to generate some activations with, the shape, the size shape, right? Like M by K. And now we're going to run 5-bit linear. So, we're sending now the activations, the part weights, the group size, the scales, and the zeros. So if I go back to my slide here, so this is the same signature that I was talking about, right? Let's look at the output. So we go back.
So actually, Manuel, before you keep going, so again, at least for GPUs, like there are certain like compute D types versus storage D types, right? So for example, you have. So for example, here in this case, like in 3 is a storage D type, and what is the compute D type in this case? And does this tend to change from, let's say, M1 to M2 and M3? Like, basically, is Apple releasing 3 bits?
So right now,
most kernels are.
Okay, so let me just then brief jump into the code then. Not this, this. Let's look, for example, so we have, some of them are optimized, some of them are unoptimized. I'm actually going to look at one of the optimized, unoptimized ones, the one that is not optimized, or like 5 bits in this case, is not optimized, for simplicity. So what we're doing is that we're doing computation, right? We are unpacking them, they're in the shader, right? And then we are doing the computation, we are actually doing over float 32, right? Like, we're doing the accumulation over float 32. So yeah, that's now the activations, right? Like, when these shaders and these tensors, they support activations to be float 32, float 16, or be float 16, right? But the actual computation happening inside these shaders, the unoptimized one, it's actually float. Right?
Interesting, yeah, because I would have expected, like, this is again me speculating. Like, I would have expected, considering Apple is really selling their hardware quite a bit for like local LM inference, that they would have added compute D types as well for like low bit D types. I don't know if this is like maybe eventually part of like their like future roadmap, but I guess this is all speculation at this point.
Let me first give a disclaimer also here, right? So these low bit kernels are definitely work in progress, in the sense that they are not completely optimized, as you can see, right? We're gonna get into that in one of the slides. And at the same time, I am still on my learning journey, right, regarding GPU optimization. So if you see something, this we know for sure this is not optimized yet. But if you see something weird, it may not be. It may just be that it's not. It may just be lack of knowledge on my part, right? So don't be afraid to call that out. But in this case, I know very well that int 1, int 5, int 6, and int 7, they are not optimized at all. I focused on enabling these kernels and making sure that they could integrate to TorchChat executors, the different surfaces where we wanted them. And then after that, I have been optimizing them. I have optimized 2, 3, and 4, but they probably can be even further optimized, right? So that's something to know. And actually, okay, Go ahead.
No, no, you go. I was gonna go to another question. Yeah, go, please go.
So actually, the structure of this talk and the aim of this talk is basically that if matching people that know a lot about GPU and a lot about optimizing them to where are these kernels implemented, how. So basically, anybody listening to this that is a GPU Perf Pro after this talk should have all the knowledge necessary to contribute to this shaders and kernels, right?
Yeah, I mean, yeah, for what it's worth, like I definitely think like the Apple's performance on PyTorch is generally something that could use a lot of love. So if you're interested in this, yeah,
I'm gonna touch on that. But yeah, I'm gonna touch on that. This is one of the things. But we're gonna go. But it's not because of linear. It's something else.
Oh, I see. Okay. So speaking of like basically maybe one question from chat that I think is a sort of like interesting segue. So George is asking, is anyone using low-bit kernels for like audio processing? Like at least like with customers that you've worked with, are they mostly interested in text, or has like audio like also came up for these kinds of applications?
So I'm not working directly with customers, but I think at least 4-bit is being used more extensively. These kernels, these 3, 4, 3, 5, 6, they are newer and more experimental. But the 4-bit has been around for a little bit longer. I think it is. And in our case, I know for a fact that we are using 4-bit for. Well, actually, yeah, I think it is. But I wouldn't be able to tell you an exact product or something.
Yeah. I mean, but presumably any customer who's using a linear, for an inference could benefit from this kind of work. So
yeah.
So another question from George. I'm going to generalize this question a bit. So like this person's asking, is it accessible outside of PyTorch? And maybe I'll generalize this. Like for example, in a lot of like custom extensions in general in PyTorch, like there's this assumption that your input is a PyTorch tensor. So basically, what is sort of the assumption here? Is it basically the input to these kernels is like a pointer of memory? Does it have to be a PyTorch tensor? And have you sort of envisioned how they could be interrupt like in other like frameworks?
Yeah. So wait, these kernels. So I wanted to add that given that they are like the shaders themselves can be used outside of of PyTorch, absolutely, right? But these kernels, they go together with op definitions, and those are right now the code that is here is for PyTorch, so A10 and executors, right? So we're gonna go into that as well. So there is there is like a layer here, right? Like we have our. Well, I'm already here, so I might as well jump a little bit into this. So we have our.
Yeah. So maybe if you could even elaborate on what you mean by op definition, I think this should make the answer to the question clear.
Let's do that, but we're gonna go back to the demos that later.
Yeah,
right?
yeah. So there's a lot of questions. Yeah. Feel free to talk to whatever you're doing.
So then let me jump then into this slide. It will be easier. So these kernels, they are under AO, Torch AO, experimental, right? And then under experimental, you have kernels and ops, right? And so ops would be your actual PyTorch op that you are registering to A10 or executors, right? And the kernel, it's tensor agnostic. So the kernels don't know anything about tensors. They are taking, in this case, they are taking MTL buffers, right? So like metal buffers. So they don't know anything about tensors, and so that's why the metal shaders and the kernels, you can use them completely outside of PyTorch, but the ops you can't, right? Because the ops are already using A10 tensors, and I mean, unless there is an integration, like if you have an integration into A10 tensors, then you can, right? But talking like generally about like general C++ code, you can use the kernels absolutely, right? Oh, wait, am I lying about the super generalization of this? Well, when we get to the code, we're gonna go through that part. But yeah, but I just wanted to make sure that it's understood that there is this separation between ops that are, that they take tensors as inputs, and then they call the kernels that take metal buffers as inputs. Should we go back to the demo?
Yes, let's do that.
All right. So, all right. So then we were on. We computed the result of 5-bit linear, and then now, so our tensor, right? So let's examine it. Has a shape 3x8. It's flow 32, and it's in the MPS as we expected, right? So now let's actually compare this to what we would have gotten if we have just run linear, right? Without any quantization, any packing, or anything. So just run torch linear, the 810 linear operator on the activations and the weights, right, on the MPS backend, and then we will get these results, which just we'll get the expected, and then I'm printing here result unexpected, and they just look the same, right? That's the same thing. So we ran torsional close, and we get through, right? So this is basically the flow that you would have to do if you want to use these operators, right? Like the quantization packing and then calling the op. So that was the first demo. Let's go back. The second demo is low bit quantizing a model. So what do we do for low bit quantizing the model? So I'm going to show it here, and then we're going to run it on the terminal. So let's use a toy model, a simple MLP, and then this MLP has 3 linear layers, right? So they have a linear layer, a nonlinearity, another linear layer, and a nonlinearity, and then a linear layer, and then so 3 linear layers connected by nonlinearity, by rails. So then, this is the only thing we need to do. So we have a quantizer that we imported from the same place that we imported the quantize op, right? So from the quant API. We build our quantizer with the number of bits that we want to quantize, the group size, the precision, and then we quantize the model. The quantizer.quantize, we quantize our model. We run. We can run the model. We can run the model through. With some inputs like this. So I just wanted to. I wanted to run this. By the way, I'm getting this error recently. Just every time that I run, that I import tertiary, I'm getting this little error. We can talk about that after.
We should fix that. Okay.
Yeah. Okay. So yeah. So I wanted to show. So this is the model that we had, right? And then after we quantize it, right? Basically, every linear layer was changed by a low bit quantized linear layer, right? And our results look like this. And our expected results are not going to look exactly the same because in this case, remember the expected would be without quantization, right? The results here would be after running the quantized model. So they are not exactly the same. So remember that when you do quantization, you do lose some precision, right? But they are they're pretty close. So that's what you need to do just to if you have a model, and this is exactly what we do when we are quantizing llama, right? For example. Right? So I'm actually gonna jump into well, yeah, I'm gonna actually jump first into the TorchChat integration because I think it's a good, it's a good connection point. So we've, for those that are not familiar with TorchChat, this is our solution for running LLMs on multiple surfaces, device, laptops, so this is the repo. This is the PR that that integrated this ops into TorchChat and into TorchChat. I'm just showing it here because it does have instructions on how how to install them in TorChat. Here is the documentation. I'm gonna go over the slides later about this too. But basically, I just wanted to show this. So actually, sorry, I actually wanted to show this code in executors. Sorry, yeah, here. So basically, this is what we do to, like, this same code that I showed there in the demo is actually what we have to quantize the model, inside the executors. Anyway, that was a small segue. I'm going to go back to the code walkthrough, but I just wanted to show you basically what you would need to quantize a model. So then the demo 3 would be running this with TorChat. Do we have any questions first, though, regarding quantizing a model?
Yeah, I mean, there's just like some discussion ranging around like what Whisper does regarding fusing matmos and kernels, but like I think nothing regarding this, so we can keep going.
All right. Okay, so for so if like I said, so the documentation on the integration with TorChat is in this link. We need to run first once you install TorChat. You need to run this script to also install this experimental ops in there as well. And then this will be how you run TorChat using this quantization. The main thing to see here would be the main thing to notice would be this part of the command, right? So it's called AFP WX, and the AFP is activation floating point. The weights are X, and this name was was chosen to have some sort of similarity to the name that is also used with the experimental CPU equivalent ops. So like the low bit, there are also low bit ops on the CPU side. These are on the metal side, right? And then you specify your bit width and your group size. So let's run TorChat with this. I just have this command here, right? Like, so TorChat generates. We are using llama 3.21 billion on the MPS device with D-type float 16, and then we are quantizing using our kernels. And let's do it. And this is definitely going to be slower than if I would be running this without sharing screen or anything like that. But let's see. I printed. I'm going to go over the numbers that we will get if we are not. So let's see how fast it does. Yeah, so this is significantly slower than. Oh, actually, no, this one it's not that bad. All right. So so I printed what I got when I was not sharing screen, and this is where we are at, right? So 3 bits, we're getting like 47 tokens per second, 49, which is more optimized. Actually, 4 bit is better optimized than 3 bits. 49 tokens per second, and 5 bit, which is not optimized, we're getting 28 tokens per second, right? So now, one thing I want to say here is, and this is regarding with what you were saying, Mark. So there are other issues with the this could be way faster, but there are other ops. The ones that are slowing us down here is actually not linear. It's actually multiplying things and adding things and subtracting tensors. So these ops are implemented using MPS graphs. On the MPS backend, they are not directly implemented using a metal shader. They are using MPS graph, and it seems to be the case that there is there is a minimum CPU overhead that you incur every time that you are invoking one of these graphs. So the experiments that I have run, the benchmarks, are telling me that optimizing those would actually what would be the main thing to speed this up at this point, at least, right? Now, for something that if for an unoptimized linear, then yeah, it would definitely have weight over this. So when we started optimizing the 4-bit linear, that was last year, we were getting only 4 tokens per second back like last year. Well, but this was not on Llama 1B. But regardless, the first optimizations did, optimizing 4-bit at that time was actually did make leaps on like. First, we went to like from 4 to 12, and then from 12 to 20, right? But at this point, right now, there are other ops. When we run, at least when we are running Llama using TorChat, there are other ops on the MPS backend that are actually the bottleneck, not linear. Does that make sense? What I'm saying? I'm gonna show you later when we are doing. Well, actually, in the next demo, you're gonna see a little bit more of that. So actually, yeah, let's jump to the next demo. Unless there are questions, let me jump to the next demo. So demo 4, it's so the intent of demo 4 is, so okay, we were here. We then is actually do some benchmarking, so I just want to compare to linear. I want to compare like between themselves, between all of the 1-bit, 2-bit, to 5-bit, right? I want to compare them. So I coded this, this benchmark utility here. Notice that I need to call synchronize. I like to call it before too, and most importantly, I need to call it after I've run my iterations before I measure the time, because if I don't do that, then I'm actually not measuring the entire, I'm not waiting for the CPU to finish, right? So, so when I run these benchmarks, something interesting. First, let me show you. We're gonna run it. You're gonna run it now later to just see if I'm getting the same numbers now with screen sharing. But these are the numbers that I got, earlier. And as I was saying, 2, 3, and 4-bit are optimized, and the rest are not, right? So you can compare with the speed of linear on a like 3 by 2042 multiplied by 2042 times 2042. So the weights will be like 2042 times 2042. Sorry, 48, right? 2048 and 2048. So the this is showing us the performance on the most optimized ones compared to linear. So you are not only, when you're using these low bit operators, you're not only gaining a lot of your reduction on memory, but also on speed. Right? Now, something I wanted to show, what I was talking earlier. So if I actually do something here, if I do something interesting, if I in my utilities here, I actually comment out this. Right? So if I don't wait for the GPU to actually finish, and I run this benchmarking. By the way, I didn't went much over the benchmarking script, but this is basically the same that we did earlier. We're just preparing the pack weights, the scales, and the zeros, and then I'm just just launching the op, and in the utilities we're doing 1,000 iterations, and we are just taking the average of that, right? But if I don't wait for the GPU to finish, which means I'm sort of measuring dispatch time or CPU overhead, right? Then look what we get. We get that linear is 37 microseconds, right? And all of the low-bit kernels are just 1.5 microseconds, right? So, and if we reduce the size, right, like go down to like the minimum basically that we can do here, like 1 by 32 times 32 times by 8, so like a tiny, like small tensors, right? Linear. So this would be if we are measuring the entire thing. So like not commenting out not commenting out this line, right? So this is the actual real time, and linear takes 24 microseconds. So it's linear would be slower than even the unoptimized tensors, the unoptimized ops. for a small input, right? For small input sizes. And if we comment out that line, so we don't wait for the GPU, still linear takes the same, right? And our ops will just go 1.5 microseconds. And so basically what is happening here is that there is this overhead. Every time that you call this op, there is this minimum overhead. You just can't get below this. And so when you have in the case of Llama, when you have linear and you have larger ops, larger matrix multiplications may not be a big issue, but you do have multiplications, like you multiply a tensor by 2, by 1, and you'll be surprised to see that this actually does happen on when you have matrix multiplication, like when you have like addition or multiplication or things like that. So right now, because of this overhead, that's why the bottleneck. That's what I was saying, that the bottleneck is not on these operators or linear when we are running Llama, or when we are running any LLM. Right? There is this issue that I put here, that is basically there's a bunch of numbers here, but basically they are doing this comparison that I just did for linear and the low ops. It's doing this comparison between for ops that are implemented using metal directly, right? Like we do have some ops that are implementing just directly using metal shaders, right? Like the low kernels are being implemented, and then this compares with the ones that are not. And basically the issue is this sort of like this minimum time, this minimum amount of microseconds, and we just don't get past it. And then what happens is, obviously when you get to large inputs, that problem disappears, right? But sometimes you're just multiplying things. You're just adding 1 to a tensor, multiplying a tensor by 2 or something like that, and you think that doesn't take, that is not expensive, and it shouldn't be expensive. But when you, but yeah, this is basically what's happening.
So for what it's worth, this is also like a very real problem on GPUs. Like basically, kernel launch overhead makes like very small tensors like not worth it. And typically, the technology I think they use on CUDA is like, instead of like dispatching multiple kernels, you basically put them all in a graph and then you dispatch them all at once. So this helps like in cases where you are very where you're very overhead bound. I suspect Metal should have some similar technology to sort of like make this simpler, but I don't know much about Metal. But
yeah, no, they do. So if you are launching the entire graph, then I think I don't. Yeah, if you have like a large graph, right, with a bunch of ops, but what happens, I think, is that every time that we are just when we're running on eager mode, right, every op that you call creates its own mini graph with just that op call, and then that's what I think is happening with these ops. And yeah, so for example, in this, what you said about the GPU itself, the GPU not being like the launch overhead, we see that for Metal as well. Like the CPU beats just directly, like a purely implemented op on Metal for very small tensors, but the launch, but the overhead is way smaller than the one that you get when you are creating an MPS graph every time.
Oh, so the overhead is getting greater. I see. So
you
need a
basically
lot of ops to amortize it.
So basically, like that's to summarize. I think I summarize it here. Is basically like for small size inputs. So this thing here, right? CPU wins over Metal and MPS for small size inputs because you don't have that. Now, for medium to large size inputs, Metal wins over MPS and CPU. And when I mean Metal, I mean like, because if you are launching an entire graph, right, with a bunch of ops, and you're doing an MPS graph with a bunch of ops, then you don't have this problem because the overhead is, it's spread through the whole thing. But if you're doing this eager mode computation, which is every time that you call an op, you launch a graph, then you have this overhead. And that's what we are seeing when we just run right now in our previous demo. We ran Torshads with here. We ran it in eager mode, right? And the ops that are taking more time are actually not linear. Actually, let me see. This is going to give you some sort of like CPU time, right?
Mm-hmm.
This is just I don't need to call it. I think this should work. Let me see. And I'm using 4. Okay. Let's just wait. I'm giving it two runs. It's going to run two times, and then it's just going to give me a profile for the last run. So the first one is just going to warm up.
Wow.
The second one, and this is going to give me CPU times, right? This is not going to give me, but you'll see how like basically the operation here is dominated, is being bottlenecked by CPU, not by GPU. Yeah. So let me make this bigger because I think it's gonna look nicer if I do so. Yeah. So you see, so this here, it's our Torch.io operator. It's only taking 1% of total CPU. Now look at A10 copy, it's taking 29%. Look at mol, right? It's taking 27%. So every one of them, so you see 35 microseconds, right? And these 35 microseconds, it's basically this. What I'm saying is basically this here, right? So it's mostly this dispatch thing, right? So yeah, so that's something that we definitely need to look into. All right, so we went a little bit over so linear demo 4. Oh, okay, yeah. So I forgot. Okay, no, I didn't forget. So this is something that after I coded this up, I realized, hey, you know what? Like I didn't compare these ops to the existing 4-bit linear that we have in PyTorch, right? So then I hacked this up today. So I just I'm going to show you the code on PyTorch later, and maybe we come back to this so you understand where this is coming from. But I did the same benchmarking with the same sizes, the same shapes that I just did the ones earlier, and I'm actually getting 72 microseconds on my machine, right? Compared to so this will be comparing 4-bit to 4-bit, right? So yeah, so the Torch.io 4-bit is actually performing better than the 4-bit on PyTorch right now. And this there are a few differences between these operators in the way that they pack the weights and how so the operator in PyTorch initially was optimized for CUDA, and then the shape, how the weights are packed, is optimized for CUDA, so it may not be the most optimal for MPS. And also the shapes, the scales and zeros are together in the same tensor instead of being separate. And then that separation, actually, we saw that it gave some improvement. So I actually thought, I knew there was an improvement, but I was surprised to see today that it's actually a little bit larger than I thought. So it's 53 compared to like 72 microseconds. So yeah, that's so yeah. So we could say that right now the best, at least on Metal, the best 4-bit operator that we have in Torch, in the whole Torch ecosystem, I think it's this one in Torch.io. Right? Now I think it's heavily inspired. This we're gonna go into when we go into the code, we're gonna see that it's actually heavily inspired by we looked at how things were being done in other places, including MLX, and it's heavily inspired by MLX's shaders as well. I am done with the demos. Let me know if there is any questions at this point.
Yeah, I guess just a quick heads up. I fixed the import.
You did that right now?
Yeah. So if you want, just like when you have time later, just like feel free to merge the PR. It should work. In the meantime, I guess like George is asking a question, which is here. Let me pull it up on the screen. Yeah. So basically asking about like pipelining kernels to avoid launch overhead as opposed to batching them in a graph. Is that possible?
I think, but that would be like some sort of compile, right? That would be like some sort of like torch compile.
Yeah, essentially.
So, yes. So and then there is work on the way. Nikita is working on torch compile, and there is AOTI as well. But I was referring strictly to the performance of Eager, right? So we do want Eager to be as good as possible, mainly because it's an onboarding tool for people, right? So you don't necessarily, like, there are faster, like with Torch Compile, with AOTI, you should get faster inference. Right now, Torch.compile, like integrating Torch.compile with, on the MPS backend, that is work in progress. And that's definitely going to have better performance than Eager, for sure. But we still don't want Eager to be super slow, right?
Like comically slow. Yeah, that makes sense.
Exactly. And if we can, if we can close these gaps by by having metal shaders that we launch directly when we have small shapes, right? Then we should do. That's an optimization that we could do, right? So we could have if the shapes of the tensors in question, of the arguments, they are under certain thresholds, right? We can just directly launch metal shaders. For bigger shapes, maybe MPS, because MPS is using MPS Graph, which uses Apple's own performance shaders. Maybe they are so optimized that then they do actually beat whatever we will have written, or whatever that I humbly wrote in metal, right? But I think, at least that's my own opinion right now. Maybe you ask somebody else, Nikita, or something, they will have a different opinion. But my opinion is that we may get a good ROI, at least on Eager, if we do this kind of thing. I don't know what do you think about that?
I think that makes sense. And for what it's worth, like George, who asked the question, like if you want to maybe reason through more about what a compiled metal backend might look like, then the right person to tag on the group is Malfet, Malfet.
Yes.
So just tag him, and I think he's very interested in this problem.
Yes.
Anyway, I think we can keep going now.
But you want to say something? So he has already worked. He has put some. There is already some PPR that he already landed, where you can use torch.compile with. He's expanding right now the support for I think I'm not sure if he's done already with reductions, but I think you can already compile a multiplication right now, for example, with torch.compile on MPS again. So you could do that right now. You can actually do that right now.
I think as you're talking, I think Nikita showed it to me. It was a single file implementation, if I'm not mistaken. Let me see if I can pull it up.
Yeah, I should have searched for this. I should have thought about this torch.compile part that we could have talked about.
Oh, but, don't worry about it. I think while you're talking, I'll just
maybe I could have made some sort of demo on that. But that really deviates right now from the lobby kernel. So I guess because I don't think there is no support with torch compile and the lobby kernel. That's not integrated right now.
All right, let's keep going.
All right, let's go. All right. So that's done with the demo part. Let's actually do the code walkthrough that I was talking about. So I already showed this slide, right, when we were jumping on this, but let's just rehash. So basically, we have on the experimental, we have these two folders. We have kernels and ops. And then on the kernels, we have MPS. We also have CPU, right? Like there are other experimental kernels that are not on MPS, that are on CPU, right? And Scott Roy already talked about those here on this channel. And then on the ops, we also have the MPS operators, right? So let's actually jump into this.
Actually, sorry to interrupt you. I found it. So I think it's
Go ahead.
It's a single file. I put it in chat, but basically, if you go to PyTorch core, it's called codegen/mps.py.
So let me. So you say
Yeah, just PyTorch core, and then it's going to be, yeah, like just go to search, and then it's going to be codegen/mps.py. It's in the inductor folder, mps.py.
MPS, this one.
Yeah, that one, yeah. It's quite cool, actually. Like, basically, maybe, like, we're not going to go through it. Maybe we can ask Nikita to come give a talk about this. But the core idea is, like, because inductor is basically it's a string template metaprogramming. And so concretely, the way this would work is every time a certain like PyTorch like operator is seen, it outputs an equivalent string for it. Like here you see this,
Right.
this string saying metal A10, and then you assemble like a metal program and you compile it. But
Yeah,
so this is that's it, by the way. This is the whole backend.
Maybe if we find the PR where, oh, that's not what I meant to do. Well,
yeah, maybe go to blame. It'll be easier to find.
Yeah.
Blame.
Add support. Maybe this one. Oh, he added reduction. But I wanted to find the first, I think in the first PR.
It's probably the one from 3 months ago, right? Implement primitive, like that one, the inductor implement, the very bottom of your screen.
Yeah.
Oh yeah, this one, yeah.
This one. Yeah, so you see that he's, yeah, exactly, yeah, this is exactly what I was wanted to find. So he has this operation, right? He's doing some indexing, then sine, then adding indexing and cosine, and then basically it compiles these things into the metal kernel. So you have here your sine, your cosine. These are the indices part, I suppose, and then this is addition, right? So yeah, no, that's pretty cool, and we are very excited about this and how this would actually accelerate, some of the the multiplications and all of that, right?
So yeah, like I think a tip I'd recommend for people watching this is that, like, I think in lecture 1, I've always talked about this very nice flag in inductor called torch logs equals output code. So if you enable this flag and then just run a PyTorch program, you will get to the generated MPS code out of it, and you can like just look at the MPS code and study it. And so this way, like if you don't have too many examples, you basically just, you see where it says compile shader, you would basically get that string in a file, and then you can like look at it and study it and profile it and do whatever you want. Yeah. It's a great way of learning a new backend.
Yeah. Once all of this is completed, I believe we're gonna also have like an integration with Torchad, and then because Torchad already supports compile for the CPU, so we probably would be able to just the same command that I had here, just -compile, right? And then it would actually compile the entire llama 3.21 billion, right? And I think that's the would be an end goal, right? I don't know if it would be compiling it into a single shader. I actually don't know if it would be a single shader, but yeah. All
right, Zebra.
All right. So where we were? Okay, the code walkthrough. Yeah. So let's. So basically, yeah. So because we want to share, and we are sharing these kernels between PyTorch and executors, we've had this design, as I was mentioning earlier, where we have our sort of like tensor agnostic code, and all of that is under kernels. Like, we're calling kernels this, like it's not an operator. Like an operator will be the thing that you actually register to the Torch library, right? So let's jump into the code. I think it's going to be easier to explain that way. So let's just go first to where the ops are registered and defined. So let's go to this file, right? So I have it open here. And let's go first. So here in this file, so under ops MPS, right? That's where we are registering our functions, right? Our operators. So notice that our packing, we have them on CPU, right? These ones we don't. I mean, we can have them also on MPS backend, but right now we have them on CPU. This is usually done beforehand, right? The packing of the data, and then we have the ones that are linear operators registered on the MPS backend. These ones, the out variants, these are actually needed for executors, and then the meta kernels. So this is where we are registering things. This is where the signatures are defined, and this is basically the op, right? So the op, well, I should have called that op, I guess, but yeah, they're being called kernels here, but they're actually what we are actually thinking as ops. They are so this is what the actual op implementation is. Basically, we are just doing a few checks, right? We're checking the arguments, and then we call this. So this is the actual what the actual thing happens. And remember, now at least I'm putting the hat of somebody that is trying to explain where everything is. So the idea here is, if anyone is interested in contributing to these kernels, this is a walkthrough so that you know where everything is located, and so that if you want to submit PRs, this should make it way easier. Well, not way easier to actually build a PR, like write a PR, but to understand where the kernels are located, where the code is, right? So then this is actually on the kernel sides, right? So this is what we call our kernel, right? So I just jumped now from the op implementation, right? So from to the kernel side, right? And then under kernels, we have our metal shaders and we have our sources, right? And our sources, we have some things that we need for metal, and we are not. So I'm gonna jump into that later, but let's first finish up with this the stream that I had. So this would be here what we call earlier on the op, right? Like the low bit quant weights linear and low bit quant weights pack, right? I think of this as some sort of like a config, right? So we have basically a configuration for each one of these kernels, and it's because if you modify one of these linear operators, you also need to, you may want to modify the packing, right? And you may want to modify the way that you're dispatching your threads, right? And so the idea here is to make that process easy, right? And give you the flexibility to actually, basically decoupling those parts of the code, right? So here, basically the low bit config, you can see that for example, for the 1 bit and the 5 bit and the 6 bit, we are using, for example, this dispatch MM, right? Now for 2, 3, and 4, which are optimized, we are using this other the dispatch. We're going to see that in a little bit in the slides, what that, how that dispatch looks like. And then we also have our packing functions, right? So then sort of like, it's like a little packet, right? Like, so you have your sort of like your metal shader, you have your packing function, you have your dispatch, right? All of that sort of like is a little packet, and there is, so basically this, where the actual thing is implemented, there is this is like the central function where things are implemented, are actually dispatched. It's completely like we don't. So it's the same that we use for all of these, for all of the bit width and all of that, right? So so if you wanted to change, for example, how you're packing things in 5, right? For the 5 bit, right? You would have to change the packing function. Maybe you don't want to delete the previous one because maybe you're doing some experiments. So you just add a new packing function, then you just change this line here to point to the new packing function. And then you're obviously changing also the shader because it's now using a different unpacking, right? and then you're, you will have to change that too, but you don't have to touch this code at all, right? So you don't touch that. So it's completely separated from those dispatch and packing elements. So so this is okay. Like as I was saying, this is what the actual kernel is implemented. Let me show you now what the packing functions are. So these are the packing functions implemented for each one of the the 1 bit, 2 bit, 3 bits, right? This is what they are, right? So if you want to modify the packing, this is what you will do it. Very briefly. So basically, the packing for 2 and 4 and for 1, it's very trivial, right? Like it's 1 bit, just everybody's in the same, like 1 bit per thing, and then 2 bits, you have 4 numbers per byte, and in 4 bits you have 2 numbers per byte. But if you're doing 3 bits or 4 or 5 bit, you have multiple options, right? And there are clever ways to do it. So in this case, what we're doing here is that we are putting the first bit of every. So we're packing, as I said earlier in the talk, we are packing 8 values at a time, and then we're putting the first bit on the first byte, right? The first bit of each of these numbers is going to be on the first byte. So you're packing 8 numbers into 3 bytes. So you're putting the first bit in the first byte, and then the last 2 bits on the second 2 bytes, right? So you have the second byte would have 4 of these pairs of bits, and the third byte will have the other 4, right? And for 5 bits, we are doing the same thing, except that you now have 1 and 4, right? And then you're putting 4 and 4 in 1 byte, 4 and 4, 4 and 4, and 4 and 4, and that's how you're packing it. Right? And for 6 bits, we are doing a similar thing that we're doing for 3, just that we're doing now 2s and 4s, right? So we're putting 2, 2, 2, 2, and so the upper 2 bits of the first number of each number in the first 2 bytes, and then the lower 4 bits of the 8 numbers in the other 4 bytes. So we're packing them into 6 bytes of them. And for 7 bits, we are, it's basically it's a little bit different. We may change. We may find that there are actually more optimized ways of doing the 7-bit, but so we are spreading one of the numbers. So basically, we have 7 bytes, right? And so every number almost fills a byte, right? You just have one spare bit on each of one of them, and then just basically spread one, one of the values, one of the 7 values across all of the bytes, right? So that's for packing, and that's where you have it. And then for dispatch, like I said, so basically we have 2. Right now we have a more a dispatch that we're using in the optimized kernels, and one that we're using in the non-optimized kernels. I'm actually going to go to the slides to talk about the dispatch, because I have. So for the 2-bit and 4-bit, what we're doing, right, is that we are actually dispatching. So think of it as you're taking basically every thread. So forget about M right now. So remember, this is the activations are M by K, and the weights are N by K, right? Remember that we're not, well, not remember, because I actually didn't mention this at the beginning, but these ops are taking the weights transposed, right? So instead of just taking N, like how you are used to, M by K times K by N, when you're doing matrix multiplication, linear is doing, and the linear op from PyTorch as well, it's N by K and N by K, right? So this dimension here is N, and this here would be K. So this is sort of how we are processing the weights, right? And the thread, what it's doing is that it's taking every thread, it's computing the values. It's actually processing the values that you're seeing there. So it's taking 4x4, jumping 128 values. 128 because 128 is 4 times 32. So we are dispatching basically 32 threads along the k dimension, and we are dispatching an n divided by 4 along the n dimension, right? Because each one of them is taking 4 elements. So then you're jumping 100. So along the k dimension, you're jumping 128 values at a time. Values of the, so like not bytes, but values, right? So then, yeah. So you, this is the dispatch that the 2-bit and 4-bit are using, and that's why. So you're dispatching n divided by 4 because along this dimension is then divided by 4 times 32 threads, because you actually have 32 threads here. So these values are for the same thread. You're jumping 128. 128 is 4 times 32. So imagine that you have like 32 threads doing these 4x4s in these spaces here, right? And then by m, because each thread is processing a separate row in the activation, right? So that's the case for 2-bit and 4-bit. The case of 3-bit, we are doing 4x8, and that's because for the 3-bit, we need to unpack the 8 bits at a time. So in the case of 4 bits, we can, with 2 or 4 bits, we don't need to unpack 8 at a time. But for 3 bits, we need to unpack the 8 at a time. And then so we are doing sort of like this. We're doing the same thing that we're doing for the 2 and 4. It's just that we are now jumping 256 because each thread is doing 4x8, right? And then the unoptimized, they are not optimized at all. So they are just, there's one thread per the k dimension, basically. So one thread per output cell. Each thread goes over the entire k dimension. So basically one thread per dot product, right? Like the full dot product over k. Right? Any questions about? I'm gonna go back to the code walk, to the code walkthrough, but any questions about the dispatch?
No, I think so far this is clear. I see one question on the perplexity, but I think actually, yeah, like maybe we can quickly answer this question, which is like, have you sort of anecdotally noticed like huge differences in perplexity depending on which like quantization scheme you've picked?
Oh yeah, for sure. Yeah. So I mean, just by running LLM, so 2 bits is not gonna like. So this is because this is post. So if we do post-training quantization, right? Then yes, 2-bit doesn't work well at all. Actually, it produces gibberish. 3-bit, it's not that bad. 3-bit is not bad. It produces, it produces good. But this is post-training. If you actually do this, if you do training-aware quantization, then things are better. I don't know the I don't know the numbers, but yeah. So right now I know that for certain use cases, which I don't know if these are public or private. I don't know. So, but
better not to comment. It's okay. Yeah.
Huh?
It's better not to comment if you're not sure.
Okay.
It's fine, yeah.
Okay.
So I guess I just want to also do a quick time check. I think we have maybe about like 15 minutes left, so I just want to make sure you have enough time to cover everything.
Yeah. So, well, we're actually almost done. So the thing that I was gonna do now was continuing basically to show the code where the integrations. So I think, let me see, we were on the dispatch, and yeah. So just to conclude, the AO walkthrough. So basically, the metal kernels are here, right? And like I said, 1, 5, and 6, and 7 are unoptimized. 2, 3, and 4 are optimized. if you are going to contribute, you would want to, like modify the method shader, say that you want to optimize the 5-bit, then you have to modify this file. You would have to modify, if you are changing the packing, then you would have to modify this file here, like the 5-bit packing here, right? And then if you are changing the dispatch, which probably will, then you also need to, you will just need to add a dispatch function here. And then in the low bit, the only thing you need to change would be this config. So that would be basically the code that you need to touch if you are going to optimize one of these, right? You don't have to touch any of the rest of the code, right? Now these ops are, like I said, integrated into TorChat, into executors, right? So TorChat, this is the PR where I think I went over this earlier. I was gonna talk about the integration. This is the PR where it got integrated. This is where they are, what is explained that basically you need to run this to install them. And here is where the integration basically it's happening. Is basically just loading. I mean, it's making the quantizer available to TorChat, right? Under this tag, this code. In executors, right? So this was the PR that integrated with the existing Llama runners. Our executors has a CPP Llama runner. There are a few more steps involved if you want to run it. You have to first follow this setup guide to to set up executors. Then you'll need to install the Llama requirements and then build executors with MPS enabled, and then build the Llama runner with the Torch.io ops enabled. And then you can export. You have to export your model, and then with the PT that gets produced, that's when you can run the executors Llama runner and generate tokens, right? And so this I showed this earlier. This is basically where the integration point is regarding the quantizer, right? So if when we are running the export, right? If Q mode would be like, so in this case, I'm using the 4-bit example, right? So this would be like Torch.io FPA 4W, and that would trigger the 4-bit quantization with the Torch.io 4-bit kernel, right? Okay, so that's the executors integration and the TorChat integration, and I mean the AO walkthrough. So the other thing I wanted to just mention is that I mentioned earlier regarding the existing 4-bit in Torch. So if you wanna, like I mentioned earlier, like I've run it in the demo, right? We run it and we compare it to the one in Torch.io. But if you're interested, the code, so basically it's here. So this is the op, right? The one defining the native functions. We also have a 4-bit in the case of in Torch in A10 we also have a 4-bit. So we have 4-bit. Sorry, did I say 4? I meant 8. So we have 4 bits and 8-bit. So all of the sort of like most of the MPS code is under this subtree, and this is where it's implemented. This is where the this is the kernel, and similarly, so this is the kernel. The shader, the shader is here under quantize.metal. So you have the op under MPS operations quantize.mm, and under MPS kernels quantize.metal is where the shader is implemented. This is in the case of PyTorch. And this thing here is because I wanted to show you. So basically, the PyTorch op, the packing is different, right? And you end up producing a four-dimensional tensor as your packed quantized weights that has these dimensions. And I believe this is because of, like initially this was landed for CUDA. And here, when I ran this demo, this is why. So when I produced this just randomly generated packed weights, right, 0 to 16, right, these are the shapes that I had to use for the packed weights. So that is, we went through the AO, we went through Toshat integration, executors integration, and PyTorch. So I put here all of these permalinks just in case anybody's interested in contributing to this code. I don't know how, like maybe I don't know. We can talk then later, Mark, how you distribute this spreadsheet or this.
Yeah, I mean, like, please send me your slides on work chat, and I'll just add them to like a repo and to your recording. Otherwise, yeah, like I really liked how you sort of gave us like an overall overview and like basically all the right places for where to look at the code and where to contribute. And so I guess like if people have questions or they want to merge some code, should they just like tag you on the AO repo, on the executors repo? Where would be the best place?
Yes, absolutely, yeah. So for anything related to these low bit kernels on the Metal backend, yes. Either if you see a problem, either open an issue, right? Like if you have a suggestion, open an issue, tag me on it, send a PR, tag me on it. Yeah, for sure.
Okay. Wonderful. Well, I think with that, like I haven't seen any questions, so thank you so much, Manuel, for coming in. And thanks for everyone listening in. Next week is actually our 50th lecture. So like we're gonna have like Omar and Jamil joining us, and yeah, super excited. So thanks again, and thank you, Manuel. Appreciate it.
You're welcome. Thank you. Thank you for having me.